Hi, this is Professor Fernandez, and in this video we are going to work out an example of using the tabular method for integration by parts. This example comes from the notes for lesson 21 in this Calc 2 course. You'll find those notes on this website along with these other resources. So the first thing I'll mention is that I highly encourage you to check out the video before this, video 21.1, where I review integration by parts, what the integration by parts formula is. You see that down here, lower right hand corner of the screen. And I also review this rule of thumb for choosing U for the purposes of using integration by parts. So I'm just going to assume that you've either done some integration by parts, you've checked out that video already, and then show you the new stuff for this video, which is the tabular method. So what is the tabular method? Let me explain it by way of this example here. Right, so we have integral of x squared e to the x on the left-hand side, and we are going to show that it equals all of this stuff. And let me just start doing this as if I were just, naively going to apply integration by parts, which would be a good thing, because this is not a standard integral. It's also not something U substitution will help with. So integration by parts is the next kind of technique to try. So if I do that and I start off on my integration by parts calculation, if I'm going to use my rule of thumb, remember from left to right, the idea here is to choose U to be the function that appears first in the integrand on this list. So in the integrand I have x squared, that's an algebraic function. I have e to the x, that's an exponential function. So I have an a and I have an e. And a appears left, first, on this list before e, in order from left to right. So the rule of thumb I late is guiding me to choose U to be x squared. And so dv is everything else left in the integrand, so that's e to the x dx. And then I just do the steps involved in integration by parts. I differentiate U, find the differential. So derivative of x squared is 2x dx. I integrate e to the x, so that is just e to the x, and then again we ignore the plus c for this purpose. So then let's write out what integration by parts says I would get if I, remember this is the integration by parts formula, uv minus integral of v du, what the integration by parts result is. So I need u, so u here, right, goes there. So that's x squared. And then I need v, so that's e to the x, that goes there. Minus integral of v goes there again, e to the x. And then du, right, so du is over here. So that is times 2x dx. Okay, and then I step back, and like I said in the integration by parts video, we now ask ourselves, is the integral that I end up with, is that integral simpler to do than the integral I started off with? And as you can see, in this particular example, the answer is kind of, right? I started off with an integral I didn't know how to do, and I have related it to an integral that I still don't kind of know how to do, right? This is not an integral I can look up or that I know, like e to the x or sine x, but it's another integral that I have to apply another integration method for. So did integration by parts help? I mean, I think it did, right? If you look at the integrals, this one had an x squared e to the x, this one has an x e to the x. So it seems like maybe if we apply integration by parts again, right, we would actually end up with an integral that doesn't have any x's multiplying e to the x, and maybe we'd be able to actually finish it. And that's exactly what is going to happen if we go down this road. And we could do that, right? But the idea is now you're applying integration by parts twice. How do you know that you don't get an integral where you have to apply it again and again and again, and you just keep going, right? So it seems like the question is arising of, if I have to apply integration by parts multiple times, is there a fast way to do this? And the answer is yes, and that's exactly what this tabular method is intended to help you with. So let's go back and redo our work, keeping in mind that, again, if you apply integration by parts again to this particular example, you will get this result, right? You saw the x squared e to the x pop out. You saw the minus 2 in front of the integrand, and we had integral of x e to the x. So if you keep going with what we were doing, you will end up getting this answer. Okay, now to the tabular method. What is the tabular method? So here's what you do. You make two columns, right? In the first column, you're going to be differentiating. This is the differentiating column. In the second column, you're going to be integrating. you need an initial choice for your u, right? So the u that we chose, remember, was x squared, and the dv we chose was e to the x dx. So you put your u over here in the differentiating column. You put your dv function, which is e to the x, over here in the integrating column. And then kind of like, this sounds, in this column, you go down a row. When you go down a row, you differentiate. So derivative of x squared is 2x. You go down another row, derivative of 2x is 2. You go down another row, derivative of 2 is 0. Okay, so when you get to the derivative being 0, you stop. And I'll say a little bit at the end of the video about why you could stop earlier than this, but we'll table that for now. So notice I'm differentiating, right, as I go down this column. On the right-hand side, I do the opposite. I integrate as I go down the column. So I start off with x e to the x. The next row down, I integrate e to the x. I get e to the x. Next row down, I integrate that one. I again get e to the x. And then next row down, I integrate. I get e to the x. Okay. And then now, here is really where the magic comes in with the tabular method. I need to multiply these terms and then change their sign. So I'm going to indicate that in the following way. So this arrow is going to mean multiply. And then you start off with alternating signs, SIGN. So you put a plus here, right? So you don't change the sign after you multiply these two terms. And I'll start writing out what the answer is for the integral using this tabular method. So I multiply these terms, x squared e to the x squared e to the x. There are, this is positive, and the sign in front of it is going to be positive. I don't change the sign. So now I do this process again, this diagonal multiplication for the next term. So here is 2x e to the x. This is positive, the whole term is positive. But now comes that alternation in sign that I had mentioned before, right? So what happens there is that I used to have a plus here, and now the next one, if I'm alternating, is a minus. So I changed the sign of this product down here. It is plus currently, but I put a minus in front of it. And that's what you do, and you just keep alternating. So now I multiply this one. The next term here is 2e to the x. This was a plus, so now this was a minus, so now there's a plus. So this term is positive, and I keep it positive, so I put a plus there. And maybe I'll put the signs in red so we can go back and review that. Okay, and then at this point, you'll notice that part of the reason that we want to get to 0 is that there's no term over here to pair it and multiply it with. We could have kept integrating. It would have been integral of e to the x is e to the x again, and then this product would have been 0. So that's why once you get to a 0 in a row on the left-hand column over here, you stop, because that is the signal to you that you're done integrating by parts. Right, so there's no plus 0 here, right? We don't need that. And that's it, right? Indefinite integral, so you add your plus c. And now let's compare, right? So we've gotten x squared e to the x minus 2x e to the x plus 2 e to the x plus c. That is exactly what is up here. Okay, and we've gotten there without having to, quote, integrate by parts multiple times. We kind of did. This is really what this tabular method is. It's taking those steps that you would have been doing, integrating by parts over and over again, and making them into this nice visual form, this table, and making use of some of the patterns that you would end up with when you integrate by parts more than once, like the alternation of these signs, SIGN. Okay, so that's the tabular method for integration by parts. It works very well when you have to integrate by parts multiple times for any function. Question is, how do you know when you're going to have to do that? That kind of comes with experience, right? I could give you some kind of general rules, but it really isn't useful. The best rule is to let the math speak to you, kind of like we've been talking about in this course. Earlier, if you go rewind the video, when we first did this integral using, integration by parts, kind of the long way now, non-tabular, we were left with an integral that we had to do integration by parts again. At that point, I would probably switch over to a tabular method. So that's the best general answer I can give you. If you're doing the integral, you've done integration by parts once, and you see that you have to do it again, unless you can tell that doing it that second time is going to finish it up, I would switch over to the tabular method. And as you go off and differentiate in this column, once you get to the 0, you will know, right, when you're done doing integration by parts. And if you keep going with the alternation of signs and all the other procedures here, then you will end up with the integration by parts answer. Okay, last thing to mention about this particular tabular method. It may seem like magic to you. It kind of is, but as usual with everything in math, there's a reason, right? And there's a nice proof, there's a nice derivation, nice explanation of all of this. And I haven't included it in this video because I'm just kind of showing you how to use the tabular method. But if you go to the lesson notes for this lesson, you'll find that on this website. Right under this example, I link to an article that has a nice proof and explanation of the tabular method, so you can see where it comes from. Okay, that's all for the video. Thanks for watching.